Good afternoon. Now, Professor Rachid Bennacer will present his speak on limits of heat and mass transfer, improvement within the complex structure. He is a professor of Des University in France. Now, please.
What I plan to talk about is something which look like more academic. I'll put some presentation because I saw that so many young staff or students prefer to remain on the dark side. So perhaps I will be able to attract them. I try to see if it works. No problem, I'll use my mouse. Yeah. Good. Before giving talk, you may saw that I am from University Paris-Saclay, which is near Paris. Then I say it's good also to present these things because it's good also to know each other. Then we come back on scientific aspect. I want just to say that previously it was federal universities. It includes also my university or previous university, University Paris-Saclay. You see the founding member, and perhaps what is important is just integrate 13% of all French research. It has an advantage because it's a campus where also companies or R&D company establish or move on the campus to create some symbiotic things. As I thanks the colleague previously from Tata who present some, how we say, industrial, but interacting with the universities. This morning we are talking between, how we say, discussion or interaction between academic and industry. I forget to mention that there are also another good formula we have in France. It's not only ministry or government who give scholarship for PhD. We have what we name CIFRE. It means that he's a PhD hired by the company and use the laboratory facilities, so he's really employee of company, use the facilities which create and emulate some subject, innovative subject and others. Some perhaps of those, I'll talk about them later. Yes. We were talking this morning between rich and poor, so I add some slide depending on the discussion of this morning. I apologize that sometimes Occidental countries or something seems somehow arrogant or feel that they are more rich. I put some slides here. I think you will know better than me. The Indian was good in mathematics. I mean the science in Europe or Occidental part is relatively recent. It is in the history on humanity, it was yesterday. So this, I like to put it like that. If there are some PhD students, what they present will be interesting, otherwise I apologize for my colleague. I went several times in China, and one saying I liked is this one, which I don't search to know the answer, I search to understand the questions. This is Confucius, or Conzi, like the Chinese name him. So today, I change my presentation and put it, I'll make just an overview, then I will discuss how can we enhance the heat transfer? And one of the key words, because this morning I saw some people that are from environmental science, some other are from process. I want to just mention it again for the young people that when you do heat transfer, you are doing mass transfer, transporting of scalar, either one or the other. They are relatively equivalent. There are some specificity, but they are relatively equivalent. For this reason, I want to say that the why is better than how. I discussed with several PhD students when I went over this journey in India, also in other places, and it's the same problem in France. Each time you discuss with PhD student on his subject and so on, he never said or answered, my good results is that things. He answered, I published this number of papers. So I continue being somehow. For this reason I said, let's make it in a journey and thinking way. Where we work on the lab, on last part of my work, I was from mechanical engineering, then I work also in environmental science and finish in civil engineering, but mainly on the building, as I said this morning, and integrated renewable energy. We work also on transfer in complex or in porous media. It could be either construction materials with specific porosity, but we did also some work on controlled porous media in order to enhance the heat transfer. So this will be my journey little by little, just to think what could enhance heat transfer. What else? This is for forget about, no need. We were talking about, sometimes people discuss what is fundamental, what is applied, and so on, which is the best. I like to say that there are all the best. Do what is useful, and so on. This is one subject. It is on more solar collector. We work on hybrid solar collectors, so they produce electricity and heat the water. We did it in a lab. We did it in situ, and we try also, when the demand is uncertain or strongly variable, we try to define the new variables. I mean, also from very applied subject, you can get beautiful fundamental subject. In this case, you see all the point you see from Belgium north, the cart which is below on the left, until Portugal. Those are all the installation we put in situ, monitor and follow, and you can find always beautiful subject. For this reason I say, if the question is well defined, then the answer could be beautiful. What else can I say? Then I was talking about solar collector. We were talking this morning about, PV cells. The good things also, I will not talk about the microstructure of PV cells. We are not in physics on this aspect. But just remember that the improvement of efficiency give us opportunity to multiply by a number of things the energy, the produced energy, electricity produced energy. I put here just plot how evolution versus technology over time it went. What we have to keep in mind is just, just look what is on the right. This is PV under solar concentration. We can reach 40% of energy. But to reach this energy, the PV cells will melt if you don't cool it. So remember that we have to cool intensively. So also if you work in several subjects, the heat transfer or mass transfer, we concentrate the energy over 100, so you have to be able to extract it. Either it is destroyed, but also if the PV is not destroyed, remember that over 67 or 70 degrees, you lose half, 0.5 of percentage per degree. It means if you have 10 degree more, you lose 5%. So you can't afford such things. You have to control this cooling. This is just to show how to enhance. It's just one example. People already did some work on metal foam and so on. I'll go faster on that. You can find exactly the same problem on cooling electronic chips because the density is increasing. So all the question I'll deal with later is how can we extract a huge density of flux and what will be the strategy. I'll teach nothing for my colleague because we know that we have to enhance the flow. If it is turbulent, it was better. Then we will discuss how can we do better eventually. It will be our challenges. The figures here shows just how the increase in the ability of compute very fast, but also in the generated energy on the chips. This that people will think that I have Alzheimer and I don't remember what I am talking about. No, it's a joke. The heat exchanger, I come back later, show that also if you have a good heat exchanger, unfortunately, and it's always the case, you work on nominal point. What means nominal point? All our optimum for given point. But generally, in a system, especially either in building or in solar, also if you do tracking, the density, the heat flux density, or whatever you want, or if it's electronic, sometimes it works very harsh and sudden demand. So remember that you create an optimal things which works only few minutes or few hours. All the other time you are out of the optimal. So the main question, how can I make adaptative system? The adaptative system will be either you change other parameters to track and remain on the optimum, or we do another strategy, you have deformable. For this reason I put these two birds, deformable. This deformable, what I show here is to insulate more, so he don't want to exchange more energy, and you will say, we wanted to exchange more energy. You see, in one case is enhancing heat transfer, the other is insulation. But if we ask a question differently, does those two problems different? The answer seems no, but they are exactly equivalent. Because what we are talking is just a porous media with a matrix and inclusion. Matrix and inclusion, if the inclusion are less conductive, it will be insulator. If the inclusion are more conductive, it is enhancing or exchanger and so on. So this will be, forget this is multi-phase flow, I think I go further. I try just to see if this will run. No, it's always like that. No problem, I have very good movies with the music. It took me a lot of time, but no problem. I'll continue, no problem. But remember, all the images I'll put later, it was from these movies, except if any young people will arrive suddenly and make it working. Yeah, I'll go through that. So remember, we want to enhance heat exchange. To enhance it is very easy in principle. We need either to increase the surfaces, but generally the surfaces are fixed. We have to increase the flow. Remember that we have duality or antagonism between increase of the flow, increase of heat transfer, but unfortunately increase in a pressure drop. What else? So the gradient will be good. I put some exchanger here from industrial to nature, and always I was exchanging with some young researcher and so on, who is the most beautiful and who is the most efficient. There are no real answer, because the answer, it depends what you want to do. I'll come back later to think in non-dimensionless way, because when we think in non-dimensionless way, what seems completely different will become exactly equivalent. It's what I want to show here. I know that it doesn't seem as heat exchanger. I make a joke on the birds, which is adaptative, but I make a joke on the difference between chicken and dinosaurs. They are the same, they are same family. Then people say, why he is talking about chicken or roast and dinosaurs? Because sometimes people, they go and study micro heat exchanger, macro heat exchanger, and the main question, are they the same or they have different things? On technological aspect, they could be different, but on some aspect, they are exactly the same thing. So we are packaging things differently to discover sometimes results which are rewritten. It's the same problem for nanofluid. You know, we have a lot of works running because we don't think in equivalent way. I'll stop perhaps on that. This is one of image from the movies. It was movies for undersea things happening. Those are a classical fins. Then people will say, we're working on energy. But this morning I say energy and mass are equivalent. Equivalent in reality and equivalent mathematically. Here there are classical fins, and if you work on fins to enhance heat transfer, I wrote that it's well known. What I mean by well known, that generally we have boundary layer classically, and we know that it tends asymptotically to some value, which is the asymptotic Nusselt value. I know that the entrance is very good, the other, it doesn't mean it's bad, but it is less efficient. positive and negative effect. It is what will I talk later, pressure drop or heat transfer enhancement. I'll come back to say, as the surface is horizontal, let's make it more sharp or more irregular or more porous media. I'll come back at the end to the equivalent of metal foam, uncontrolled metal foam, but what we have to keep in mind that I want just to increase it because it's fins. If you see the fins, the classical, those kind of things, I guess is this one. A classical, same mass. If it's not same mass, I have to define another things. Triangular and this. If we look on the efficiency, I know that you have here the color. The worst is this one. This will be better, and this normally will be the best. Except that depending on the flow, this is what we teach to our student, in some part this is better, and some part this is better. For this reason I was talking deformable things. When we finish the discussion, we will eventually say what is the reliable, what is the life duration, and so on. But just remember that also when I optimize something, it could be optimum here, and you see it is less good here. Moreover, remember that when we study this analytically, the flow is constant and the H is constant. In reality, the H is depending on all the position, and any change will change things. We can extrapolate from this system to those systems. They are equivalent. If I go like that, what I am talking here is those are 1D regular. This is 1D, or let's say it 1D homogeneous, 1D inhomogeneous, 1D inhomogeneous with given shape. So I'm using word just how complexity I am putting inside. If you see this, some people will say 1D inhomogeneous, the shape is changing. This is just to reduce the pressure drop. You see this was for cooling processor. You see they add the shape special way that the air is flowing here and less drag or less pressure drop. What we have to keep is the H here is different from the H here. This could be better than this and so on. But remember it's 1D, 1D. Inhomogeneous, inhomogeneous in 1D or inhomogeneous in space. This, which seems complicated, or this one, there are 2D. Then you have some people who already analyze and sell and install these kind of things. It seems 3D, but in reality it is a 2D because it's just extrusion. It's a 2D inhomogeneous. Some other people, they came, and it was very, how we say, it allows a lot of things. They came and used metal foam. And you have several, I say metal foam, but it could be ceramic foam and so on. It depends what you want to do. It could be a process, it could be catalyst, it could be heat transfer. When it's heat transfer, we will use mainly something which is high conductivity. So remember, this is 3D homogeneous. So this normally seems better than that. What is the advantage of this? One of the advantage is the turbidity, I mean the mixing. You remember when we work on a flow around cylinder, very early, after a few Reynolds 1, began the transition to the tail with the vortex appearing. So you can have more mixing in this one. Some people will say it's turbulent. Sometimes I say, let's perhaps discuss and define what is turbulent. I can have just small vortex which are determinist and well structured, and the interact of them go toward chaos, but at the instantaneously we are not at the huge really number of classical turbulence. Okay, just so what we have to summarize: 1D, 2D, 3D. Sometimes homogeneous, sometimes inhomogeneous. What I'll come back later, I come back to work on 3D inhomogeneous porous media. Let's continue. What I put on this side is, I know that I have to do that. I have to be aware of that. This allows to reduce, especially if it is mobile, something moving. This, I agree with you, recycling and so on. I am talking about cost function. Cost function, you can include whatever you want. What I want to do is to create something not working at nominal point, but due to some stress, external, it adapts, and my gap of working could be that. This will be the deformable or other, we will come back later. This I can continue. It's what I am talking, change in space. This is classical. Classical, yeah. As we finish the 1D homogeneous, partially no. Those are another, unfortunately, beautiful movie you didn't saw, Under the Sea, with the nice music. If someone is interested, they can show him later. So I wrote it's partially known. It's not classical fins like what we saw. You see it's special fins in cylindrical way, structured in some way, but we can say that it's 1D if I am cylindrical, but inhomogeneous. Some people say, but there are no heat transfer. It is exchanging some nutriment and some other things. It is, instead of scalar T, it is a scalar C, concentration. So there are equivalent for me. Let's continue. Yeah. Perhaps just before, I want just to mention this convection diffusion, the asymptotic I already talked about, this entrance, and the asymptotic classically, this was for most students, but for us, we will see mainly this. Perhaps I remain just on this. 3, restructuring flow using complexity. The anti-baffle is another things on which we put patents. We will discuss if we have time. The ability of computing now, you know, if you put a hole, this is classical 1D, if you put a hole, you are structuring it in 2D, you are modifying locally H, and you are increasing the apparent section. This is just to show this. This is extrapolation of that. We can compute, this is one of my master's and PhD student working, this was another study before. I mean the power, the possible computing, no problem. Here it was to show how the flow is going and how it became unsteady. Sometimes the video doesn't pass. I just show this in another group working. This is 3D. Some people will say 3D inhomogeneous. Yes and no. Because you see it's metal foam, but they structured and cut part of it. It looked like this, fins, and they put holes in fins. Is it inhomogeneous? The answer is yes, it is inhomogeneous, but there are some problem or some limitation on that. When you put a huge opening, the flow will run and pass over that. But it reduces the pressure drop. So this is the advantage. So what is the compromise? It means that we have to find how much was filled with metal foam, how much I can let it for the flow to pass. This compromise will be one and unique optimum, and it'll have more power exchange. You know, sometimes you'll see some message like that. Generally, it's for me, because sometimes I pass very fast. Good. This, now I come back to the heat exchanger. People who do numerical work, this is just between bracket. I added just for students to understand that people interested by porous media, they use it as one phase. This is reality, this is grid, this is 2 equation. Perhaps people who did this is equilibrium, thermal equilibrium, 1 equation, 2 equation connecting, and the direct numerical simulation. What I'll present here, what we are doing is this one, for where we can come back to what is the limitation of this and what is the limitation of this, if we have time. This is classical joke. This is Navier-Stokes. This is turbulent chi epsilon less, I less, and so on, with all the coefficients to fit with the reality. If you want to make a joke, I hope I didn't lost all of you. Laplace, I didn't put his photo in the beginning, was very good in mathematics. He said, if you want to draw a line, you need 1 coefficient. Surface, 2 coefficient. Volume, 3 coefficient. Elephant, 4 coefficient. Dancing elephant, 5 coefficient. You see? And sometimes the student, when they work on turbulence with mu1, mu2, F1, F2, sigma, and they come back and say it doesn't fit. Somewhere the physics lacks somewhere. But it could be also an experimental work, and they can, because they don't use just dancing elephant 5 coefficient. If you have 9 coefficient and you don't fit, perhaps the strategy you are using is not good. I stop my joke on this part, and I continue. Yes. I continue and arrive. The only things I want to develop here is how we create porous media and control it. In reality, metallic foam, you can create it. We want porous media, which is not homogeneous locally, but I want it statistically homogeneous or inhomogeneous. It began being perhaps ambiguous. What I mean is, if you remember the transition on Reynolds, I don't want metallic foam. I want metallic foam over distribution, not all the same cells. How we do it, I'll show you something. You see this mountain? If you put threshold here, you will see this one. If you put threshold higher here, if I cut here, I'll see only black and white everywhere. I think I have more simple. Yeah, this is better. Look, this is 1D distribution. If I threshold here, it will be black, so solid. If I threshold here, it will be black and white, some given porosity, less porosity. If I threshold here, it will be fluid. So you see, with one distribution I control. I can create solid or fluid. And when I pass from solid to fluid, I fit with the same distribution. This is 1D. I come back to previously. This is 2D. When I say 2D, it means x, y, and then I have functions. If it fits with my distribution, when I cut the porous media I find here, it will fit the distribution I put here. Also, if I cut higher, all structure remain on the same distribution. So I am controlling different porosity of porous media, which is locally homogeneous, but fitting with distribution. I want to take time for that. If you understand the 1D, this is the 2D. Now try to imagine you have a distribution in 3D. 3D distribution is this one, which means that you have x, y, zeta, and variable as distribution. It's what you are using to do when you plot isothermal on 3D problem. When you say, I want to plot the temperature 20.5. In 3D, you will follow this one. This is the 3D distribution. When you threshold this distribution with the variance, eventually length of correlation, this is details, you can find this structure. This structure, if you see just here in the middle, you find this, because this is distribution in 2D, this. If I see distribution in 3D, it is this one. I am generating a porous media under controlling distribution, with the same distribution, different porosity. It's the example I show here. It's different porosity from low to high. I can continue.
Excuse me, Professor Rachid.
Okay, good, thank you. When we understand that, I can go very fast. Those are numerical results, it's details for us. I go on that. What happened? I add another complexity, which is, if you see in nature, the heat exchanger are inhomogeneous, not inhomogeneous in distribution and globally homogeneous. They are inhomogeneous in space. We want to control what you see here, this homogeneous, this is inhomogeneous. So we are creating structure we control over space. Then some people will say, yeah, but what will induce the heat transfer and so on? I agree with you, we will come back to that. But what we are saying now, I give degree of freedom to generate structure analytically, threshold them, homogeneous or inhomogeneous in 3D. The other is just algorithm of optimization. Under some constraint, find the best one. I want that we explain what is the first level, what is the constraint, what is just the consequence. I continue this, how the student went over it, how he create inhomogeneity, how he compute, and so on. I go through that. This all is blah, blah, blah. This, for example, is memory 4. Because sometimes over one critical point, I want to change my structure to avoid the, how we say. Okay, this, if you want question, we'll come back. Here I insist for one thing. This was a paper for electricity. You see, it's not an energy at all. People are using metal foam. If you use metal foam, you can create B-material structure. And I come back later because the printer now allows. We work on B-material structure. If it is with phase change, he can store or restitute energy. But if the shell is deformable, when it melts, it will change the form. I show you an example. This one, look. You remember, with the threshold, we are able to create this one, the red one, plus the blue. If I threshold again, I am able to create the secondary structure. So I am able to create one structure inside the second structure. The printing now, the 3D printer work relatively well. So if you have just two colors, you are able to print those. I am going in through my journey, you see. I'm making 3D structure, which could be inhomogeneous. Now I add functionality of something inside, deformable and non-deformable. This will be micro-exchanger. This is macro-exchanger. This is technologically complicated. It is equivalent. But in reality, it is easier because it's laminar. I mean, on difficulties, it is this one, working at very low Reynolds number. Just this is my joke of that, and then I'll not continue the experimental. When you admit that we have a structure with a liquid inside, you see, we were previously working on a fins to enhance heat exchanger, where inside I have two colors. When you admit the existence of fins with a second inner part, with a flow outside, you can consider that the secondary flow, the second material inside can flow. What I present here is exactly what I present previously. One flow can go out of your fin. As your fin contains secondary material, it can flow. We pass from fins to heat exchanger. It was a fins 3D volumetrically structured. It became heat exchanger 3D volumetrically structured. What you see here is a double cross. We are generating a structure which is, you see here, we didn't yet print it in metal. It is in let's say, classical PM. I have some here if you want. Then we have the good things is that volumetrically you create and separating things where you control exactly the size of the inner, the width, and the outer. So it is just a process in reality. When you understand the concept, then it will be better. Some people generally want to know if my movies work. This is this one. This is structured. This is the inhomogeneous. Those are the deformable. These are the heat exchanger. We got just some problem. This is our 3D metallic printer. Unfortunately, it doesn't, what we got doesn't fit very well. So this isn't, I don't present. I have only few of them. What you see here is the experimental work with classical surfaces controlling different porosity, and this is the experimental apparatus, and I think no need to go further. What can I say? Perhaps I finish with that. Hard or easy if the chairman agree. This we saw that there are equivalent. This is heat exchanger, but it could be in the 3D structure heat exchanger volumetrically. I was discussing that it's heat exchanger, but normally there are no obligation. It could be catalyst. When you work on reforming, I know that India, there are several labs working on reforming. I can have, and recovering some part before, I can use catalytic external, catalytic on inner part, and I am working because one is exothermic, the other is endothermic, and previously we have to bring energy and cool the other. By this system, you use a double catalytic surfaces, and in two level of process, coupling them like the classical heat exchanger. Here it's a mass, reactional, and heat exchanger. I finish with this bad joke for some PhD students who their life remained sticking to computer, looking on screen, and trying to get the answer, but they don't ask themselves if it is the good question they are asking. Thank you, dear Chairman.
Thank you very much, Professor Rachid. But due to the paucity of time, we can ask only one or two questions from the audience.
It means I was not very clear, huh? Thank you.
Sir, I am to improve my understanding of whatever you have spoken. I just want to improve my understanding. Is it the changes in macro level or micro level, or both?
Or if you hear me, I can answer from here.
Pardon?
You can hear me from here?
That is macro level or micro level?
Thank you for the question, and I didn't expect so good question because I forgot to mention that. Some people work on macro channel, and they come back, they say, work on macro channel. And my question is, what is the size of your macro channel? And I make a joke because long times ago, in the beginning of 2000, we work on macro channel, but we fake the system because our macro channel was 900 micrometer, which means almost 1 millimeter. So the question micro or micro, it is a concept or what? Where you are right, it could be micro when the continuum equation stop being good and mathematically we change, rarefy something, we change the equation and the boundary condition. If I am in this amphitheater and I create a void, I'll ask people to get out first. I close all the door, I put a big pump, and I take all the air. I'll be in micro channel. On this size, it's micro channel. Because as I have less and less air, less and less mass, I have a big mean path. I'll be as in macro channel. I can go in micro channel, increase the pressure, and I am in macro channel. So you are right, is the Knudsen number below or higher? Well, what we did numerically, the structure has no difference because what we structure, the printer, we are limited by the resolution of the printer. The printer we use is able to work no lower than 0.5 millimeter. When the printer will improve, we can go lower. So the structure we are creating, it could be big toward the small, but we're still limited by the ability of the 3D available printer. Is the physics we are studying continuum, like macro channel or micro channel? I prefer to say below or above given Knudsen number, because it depends on temperature, pressure, and so on. What we simulate and my students simulate, it's always slip boundary condition, continuity in temperature and flux, so we are in macro approach on fluid flow and energy.
Okay,
Well,
thank you.
the second question is, if we take this macro level,
So
then suppose the recuperator, regenerator in furnace.
one thing there, just
Furnace, recuperator and regenerator. We have got the porosity there in recuperator or regenerator for heat exchange. In case of microstructure, say in case of a carbide structure within ferrite, so if it is not homogeneous, then heat transfer is or mass transfer will be inhomogeneous. So it is homogenization what we do for better heat exchange. Homogenization by heating, in heat treatment,
Okay.
in microstructure, micro level, but in macro level it is just the reverse. Because we are doing
Excuse me, sir.
porosity
Excuse me,
So,
sir.
to-
Okay.
You can
I-
discuss all these points
I
during the
can- I
time of
can-
tea time.
I can give just fast answer. You remember I say below the Knudsen, critical or above. I'm talking physics. When I talk about flow, I talk Reynolds number because it's velocity versus viscosity versus the size. Then it is correct. When I talk about fluid, I'll say prompt number. How will do the boundary layer, dynamic boundary layer versus thermal boundary layer. So if I have to discuss, continuous or not, this or this, how is going laminar or turbulent or turbidity,
No,
I'll talk
think
about
that
Reynolds.
is your
In
method.
homogeneous is same story. If I rewrite my problem, if my physics remain in continuum, it is equivalent and generally micro, I can do it with micro and so on. If it is nanotube and so on, we never went there, and we will never deal with that.
Thank you, sir.
Okay,
My pleasure.
Thank you very much. Thank you, Professor Rachid, for your very good lecture. It was a very informative lecture, and we believe we will be enlightened by your lecture.
Yeah.
Thank you very much.
I hope that the colleague or student understood that it was more questionable question, how can I go when I put the good question, how things are structured. Some heat exchangers and fins, which is surfaces, are exactly the same, and the question behind is when we teach it also, this is contra heat exchanger, if you make different level, you find isothermal, which became fins. So we pass from heat exchanger
yes.
to fins. This was, I wish.
That is very good. Thank you very much, sir.